Hi, in this video lecture we are going to learn about state reduction of state and flow tables. On completion of this video lecture, the learners can able to understand how to reduce the state table and how to write the flow tables. So, reduction of state and flow table, the procedure, there is one particular procedure for reducing the state tables. Using that particular procedure, the number of states, internal states used in an asynchronous sequential circuit is reduced. So, this reduced circuit resembles the procedure that it is used for synchronous circuit. This is the main logic used in this one. By using this implication table, it is reduced. There is some step by step procedure to reduce this state tables. So, initially how we are going to see how this state tables are reduced, the initial steps. So, before that the flow table should be realized and it should be reduced. So, the first step is to understand the process of minimization of flow table, and using this example this flow table is realized. Now, drawing the state diagram and derive the primitive flow table and state diagram above for this circuit given. So, place a cross in any square corresponding to the pair of states whose outputs not equal for every input. Then for second state, reduced primitive table is drawn. So, after drawing this reduced primitive table, enter the remaining squares of the pairs of states that are implied by the pairs of states representing the squares. Now we can get the maximal original states resulting in reduced flow tables. Now, in the state step 3, the state assignment is done. In order to obtain the circuit described in the reduced flow table, it is necessary to assign the distinct binary value to each state. This assignment converts the flow table into the transition table. So, here making successive passes through the table to determine whether any additional squares should be placed within the cross mark. So, reduction of state flow tables, merging the flow table. So, the process that must be avoided, the process that must be applied in order to find the suitable group of capabilities for the purpose of merging the flow table is divided into two steps. So, first step is determining all the capable that is all the compatible pairs by using the implication table. The next is finding the minimal capabilities using the merger graph, and the third one is find a minimal collection of capabilities that covers all the states. That is the third one. Now all these steps are done for finding the primitive flow table. So, we can also implement the circuit represented by the transition table using some particular latches. Reduction of primitive flow table, the merger graph gives two compatible pairs as a set of maximal capabilities. For example, AB is equal is S0 and CE is S1 and DE is S2. The set of maximal compatible covers all the original states resulting in the reduced flow table. So, in state assignment, if we assigned S0 equal to 0 0, S1 equal to 0 1 and S2 0 0 1 0 and S3 1 1. So, S0, S1, S2, S3, then the state assignments will be S1 to S2, S2 to S1, like that way it is routed. So, here the reduced state table will follow the flow table. From the flow table we can by using the merger graph we can find all the synchronized data synchronized circuit. So, here critical races and hazards that may occur, to reduce that we are implementing the reduced flow table for finding the final stage. So initially the step-by-step procedures are followed, and if we assigned the different S0, S1, S2, S3 values, we need one more states to prevent critical race during transition. Introducing another one state and are routed through the new state. Therefore, the state assignment can be obtained in order to attain the critical race, in order to avoid the critical race, and described by the reduced flow table, and it is necessary to assign the distinct binary value also. Like this way, the reduced flow table can be obtained. The two states are compatible if in every column of the corresponding rows in the flow table there are identical or compatible states if there is no conflict in the output values. So there will be a tick mark. The reduction of state and flow tables are calculated by this merger graph. So each and every state it is connected with these lines. It can be avoided if it is repeats, or otherwise we can find the final reduced table. So that's this asynchronous logic circuit. The flow state table and flow tables are reduced to make easy for this circuit design. Thank you.